Welcome to Saxy's Pre-AP Chemistry's podcast. This is our first one of our Unit 3, and we are going to be looking at the electrons. So we told you, I'm sure Mrs. Fisher also told you that we kind of ignored the electrons for a while in the atomic structure, focused on more protons, neutrons, and said we'd be spending more time talking about electrons because they are what determine the the chemical reactivity. Well, now's the time that we're going to look at it. So what we're going to do tonight is kind of relate to the dorm activity that we did in class today to what actually has to do with electrons. We're going to relate the activity we did today and what it has to do with electrons and chemistry. So let's kind of go back to what you know, the Bohr model. Bohr model, I know you learned in 8th grade, and it's actually, okay, let's go to the Bohr model. This is what I know you probably learned in 8th grade. We talked about the electrons, Niels Bohr, and we will spend a little bit more time of how he came up with the Bohr model. Talked about electrons being at certain energy levels. And at these energy levels, they were like orbits that travel around the nucleus. So if I looked at this, I know that this is chlorine, 17 protons. And so if I looked at this, there's electrons that have the same number for right now, because we're not talking about ions, same number of electrons as protons, and they're circling it on orbits. Well, this worked great for hydrogen. Unfortunately, there were some problems. It didn't explain the chemical reactivity of all the elements, and it just didn't work for anything really very well past hydrogen. So they had to come up with a new model based on the experiments and based on results of the Bohr model. What do you need to write about that? Talk about orbits. It actually, a lot of times we will still write it as the Bohr model because it is a very good job of explaining and we're going to show a correlation between the Bohr's model and the quantum model. But let's look at what we're using now. Quantum model. Okay, this is the modern theory we use today, so I would write that down. I would have probably drawn in a Bohr's model. If you hadn't already, pause it, go back. Difference, electrons exist in a three-dimensional region known as orbitals. Look at how I've already highlighted that. That means to me, I would know that word. You need to know what orbitals means. And what is it? It's just that three-dimensional region. It is a mathematical model. What it is just a probability of where an electron is going to be at some time. Now we're still going to have those same energy levels as the Bohr model, so sometimes we'll do that correlation and kind of show in a simplistic way the Bohr model, because the reality is it's just too hard to try to draw it in that three-dimensional area. Now, if you look at this mathematical model, you're probably going, oh my gosh, dimensional analysis. No, it's mathematical model beyond what we are going to be doing. So we just need to realize that it is a probability that where that electron is at some time. Okay, so we're going to look at some pictures. Now what this picture is, if we look at these dots, it looks like this is an electron. Notice I said an electron, a electron. This is one electron where it is. We could take a million shots, or as Mrs. Fisher says, a bazillion shots. And so pictures of it. So we're just trying to look at where is this electron most of the time. Well, most of the time, hopefully you can kind of see the shape right here. This is why we say this is our first shape that we're going to be calling. This is called a s orbital. So where you have orbital shapes, see where you have an S, you need to write down a sphere or draw a sphere. Again, hard to do three-dimensionally. You could draw it as a circle, maybe kind of put underneath it that's a little sphere. Now don't get too worried about drawing some of these other ones. You just need to we'll look at how many orbitals we have. Well, look at the first energy level, just like in Bohr, we have a sphere. At the second energy level, we also have another sphere, but if you look at this a little bit bigger area, this would be my 1s, around here would be my 2s. Well, let's look at some dots of another area that we have. So we're going to fill electrons in our s. Look at what happens when I look at some dots. So let's look at some of these dots. Okay, again, look at this area. It kind of has a void in the middle because this is where the S is going to be. And so if we look at, where the probability again are we going to find the electrons? We have two areas. Up here is an area, and over here is an area. So, oh, look at how I'm kind of drawing this area. So what do we say that those look like? They look like, okay, now I've heard them called peanuts, figure eights, dumbbells, snowmen. It's what kind of sticks in your head. But what do I know? I know that I have three P's. That's what's important. I have one that's along the PX axis, one along the PY axis, and one along the PZ axis. Because again, we're three-dimensional. But what do you need to know? There are three different P orbitals. Okay, so look at my third energy level. I still have an S. There's a 3s. That's going to be just a little bit higher, a little bigger, because as we get to a higher energy level, they're just getting further out. They're not wanting to show. Here's be my 3p. Okay, this is a 3p. Again, they're just getting a little further out. Okay, what do we have? Well, we have some d orbitals. And look at these. They're starting to get into the quadrants. So these are all on my quadrants. Don't try to draw these. You don't have to kind of draw these to look at what they are. I mean, if you want to attempt to. But what do I need to know? That there are 1, 2, 3, 4, 5 d orbitals. And again, they're not balloons that are holding these. This is just the probability. This is the area that there's the greater probability to find an electron. Thinking again that we're looking in the three-dimensional. So I have one s, there's one s orbital, 3 p orbitals, 5 d orbitals. Are we seeing a pattern? And look at again, at the fourth energy level, there's a 4s, a 4p, 4d. Are we seeing how they're building? And then we have f's. Then we have our F's. Again, they're not all pretty golden bronze colored. They're just using these colors to represent the different areas. As you can see, they're starting to get more and more complex. That you're having it's again the probability where those electrons are. But what do I need to know? There's 1, 2, 3, 4, 5, 6, 7 F orbitals. Again, I want to try to draw these. So on your sheet, you should have had that there's an S. Then I had it out, the PX, the PY, the PZ. Then you need to know there's 5 Ds and there are 7 F orbitals. Okay, what else do I need to know about those orbitals? Add this underneath. That in the 1s, okay, and relate this to what we were doing in that auditorium. Think of that little GISD dormitory when we were talking about the S suite and how it could hold only 2 people. Well, you know what? The people were electrons. So in an S orbital, there's one orbital. That was the bed. It can hold 2 electrons. That was the people. Remember the P, there were 3 orbitals. The 3 beds represented the 3 orbitals that could hold a total of 6 electrons. The D has 5 orbitals, each can hold 2, that can hold 10 electrons. The F, 7 orbitals that can hold 14 electrons. Write this down. You need to know this. So why are we doing this? What is the benefit? Well, it just, like we kind of So let's also make sure you write down somewhere there that you have the different energy levels and you need to know how they build. So at the first energy level, which is very similar to the same, so let's look at those electrons in the energy level. Again, it's very similar to the Bohr. We just realized Bohr was more on a single track. We're realizing quantum can go more in a three-dimensional. But we still have a first energy level. The lower the energy level, the closer to the nucleus. It's tighter, it's smaller. There's only the 1s orbital that can hold 2 electrons. We go a little bit further out. We have the second energy level. Look how it repeats. We have a 2s orbital and we have a 2p. So this, if we remember that we looked at it, this 2s can hold a total of, what do we say, 2 electrons, and this 2p can hold a total of 6 electrons. So you add them together, that's where we get our 8 electrons. Look at the third energy level. We're going to add. We have 2 electrons can go in the third energy level, 6 electrons can go in that p, and what did we say? 5 times 2, d, can hold 10. So this is where we get the 18. At that fourth energy level, The S is still there that can hold 2, the P that can hold 6, the D that can hold 10, and then we said there were 7 Fs that could hold 14. And we add all those electrons together, that's going to be my 32. Notice, this number up here is going to be signifying number of electrons. S, what orbital? 2, what energy level? So let's write that down too. Let's kind of compare why we're using this. Again, the Bohr model, it works well, but it is very simplistic. But it works really, it only explains the chemical reactivity for hydrogen, but we know there's a lot more atoms than hydrogen. What's the difference? The Bohr model, we call them orbits. In the quantum, we orbital, and it's again three-dimensional. And the Bohr model is the quantum model is a probability. It's a mathematical model of where you think those electrons are going to be. And again, the Bohr didn't explain all the behavior that we were seeing. So we have rules, just like you had rules that you had to do in the dormitory today. Different rules of how we fill it up. So if I look at this, this is the energy level that was very similar to what you saw. You had to subtract with the energies to see lowest energy first. Well, there's a pattern. First I can fill a 1s, then a 2s. That makes sense. And I can go to a 2p, then a 3s, then a 3p. But look at what happens here. Something kind of weird happens between this, because I'm going to fill a 4s before the 3d. You should have seen that when we were filling in some of the electrons, or excuse me, some of the people that were really kind of representing our electrons. They went to that little suite before they went to the big suite because it was cheaper, if we want to think of it as money, or less energy. Well, another way you can see it is you draw yourself a little chart and you follow it. It's like the bouncing, follow the arrows. I'm going to put them in a 1s. Then what do I go to? So I go from a 1s to my 2s. Then it's full. Then I'm going to go to a 2p, then a 3s, then a 3p, 4s. Then I have to go to a 3d, 4p, 5s. Then I come down and I'm filling it in. Yay, awesome. Okay, I have a little tool. I don't want to draw this on every test because I'm not going to give this to you. I'll be honest, I'm not in love with this. There's got to be a better way. Let's look at a better way. Okay, now if you notice, I'm going to kind of skip the quantum numbers and the atomic orbitals. We'll kind of talk about that, so don't let that freak you out. So go ahead and turn to the top of the next page, and you have a periodic table, and you have a little periodic table on the bottom. Well, your little periodic table is actually in color, but we can't copy colors. What yours kind of looks like there. So I want you to color your periodic table like I've done. So it doesn't have to be exactly the same colors, but you need to color it the same. Meaning right here, look at the first two rows, and look at helium really should be over here, same colors, and we're going to call this the S block. And look at 1, 2. 2 electrons can go in the S, and I have 2 columns. Okay, 1, 2, 3, 4, 5, 6. This area over here is called the P block. Look at my blues. 1, 2, 3, 4, 5, 6. There's 10. This is called the D block. And my green, if I count it over, there's 14. The green is called the F block. Now notice up here, I've got these numbers, so that everything in this column is going to end in an S1. Everything in this column is going to end in an S2. This column, P1, P2, P3s, P4, P5s, P6s. It's full because 6 is the max. This is full at a 2. Okay, D1 all the way to D10. 10 is full with the D. I'd be full. And then an F all the way up to an F14. So what we're going to do is just give them a home, just like we did, and when you get to the end of a block, you're going to have to start over in a new block. Now with your energy levels, let's look at this. Energy levels, they're the same as the periods as we go down for S and P. So this is a 1s, okay, this then across here would be a 2s, these would be 3s's, 4s's, 5s's, 6s's, 7s's. P's are also the same. These would be a 2p. And this is what that little one down below is showing you. Look at the picture down below. 3 P's, If I go over to this one, so let's look at this. 1s, 2s, 3s, 4s, 5s, 6s, 7s. Okay, s's and p's are the same. S and p's are the same. Same energy levels. Okay, look at my d's. D's are always 1 minus your periods. So this is on the 4th period, the D is always 1 less. This is the 5th period, or a 5s, 1 less. Because this is the first place you get to a D orbital, is at the 3rd energy level. Okay, look at our F's. We'll spend a little time looking at the F's. Remember, if I could stretch out the periodic table, this is really where it belongs. So the first place we have an F orbital is on the 4F. So that's where this is going to be. Okay, so what we just kind of need to do, and again, I'm not going to talk about the quantum numbers, we'll kind of talk about that a little bit later. Let's just use your configuration, and let's use the periodic table. And I'm going to go right here, and let's write some configurations. So I have hydrogen first. Okay, I would have your own periodic table out there. You can look, because I know that hydrogen is right here. So what is my configuration? I'm going to write it as a 1s1. What does this mean? And I would write down a key right now for what this means. Okay, the little superscript stands for number of electrons. The S is the orbital that it is in. The 1 is the energy level. Okay, kind of when we're talking about our address, we're just getting more specific as we start to give it a home. And that's what we're doing with configurations. We're just giving the electrons a home. So I have 1 electron in the s orbital on the 1st energy level. This is the configuration of hydrogen. Okay, helium. Well, here's helium. Okay, now the nice thing is we have to give them all electrons, but we don't always have to. We have to start up here at the top. But I don't have to say 1s1 and then 1s2. We say the total number in one orbital in an energy level. So there's 2 electrons in that 1s orbital, so I would say that there's 2 electrons in the s orbital on the 1st energy level. I'm done. It's full. Okay, we're going to start reading like this, like these old typewriters. Okay, lithium. Well, lithium is right here. It's my 3rd electron. It's my 3rd, element. Okay, I still have to start at the top. So I'm going to fill it up and say, okay, well, this is full. So if it's full, I have to write it down. 1s2, then it's full, go to your next level. What do I have? It's going to stop right there, 2s1. So the configuration of lithium is 1s2, 2s1. How do I know? Do I have a double check? Yes, add up your superscripts. They have to add up to the element number, the atomic number, which means it's adding up to the electrons. Lithium is atomic number 3, therefore 3 electrons. I've just found a home for all 3 electrons. Okay, beryllium. Beryllium is right next to lithium. So what do I know beryllium is? Well, I have to always start at the beginning. And when I go all the way through, I just list it as full. I don't have to list every single electron in that orbital. I just tell you when it's full. This says that the 1s is full. So I'm going to my next one. 2s, well, there's also 2 in there. So now it's full. Okay, well, let's see. How about then nitrogen? Let's kind of skip. What if I'm going to nitrogen? There's nitrogen. It's element number 7. That means there's 7 electrons I need to give a home to. I have to start in the beginning. So what do I know? 1s2. That's full. I have to go start all over. Start at the next energy level. Next energy level, next orbital is a 2s. It's full. Full means it can hold 2. Then I'm going to get to a 2p, and there's 1 of them, 2 of them, 3 in there. So I'd end at a 2p3. So look at, there's 5, 6, 7. All 7 electrons have found a home. Magnesium. Okay, where's magnesium? It is right here. Okay, this is my endpoint. I get a periodic table, I put my finger on the element, and I'm going to work my way down to it. So start at the top again. Are we seeing a pattern? 1s2. Then what do I have? 2s2. Then I have 2p6. What's next? 3s2. I'm going to stop right there at 3s2. Okay, and I double check. 8, 9, 10, 11, 12. Magnesium's atomic number 12. I have 12 of them. Okay, let's go to iron. Iron is 1, 2, 3, 4, 5, 6 right here. I can't just end, unfortunately, on that. I have to still start at the beginning. Let's put it up here. Iron, where am I going to be? 1s2, 2s2, 2p6. Okay, 1s2, 2s2, 2p6. If I stopped right there at 2p6, that would be neon. But I'm not done. So where am I at? 3s2, 3s2. Then what do I have? 3p6. Oops, I'm running out of room. You should have this all in one line. Sorry, my fault. 3p6, because I'm going to run out the screen. Where do I have next? 4s2. Okay, then remember we come to a 3d. D's are one less than your S's were. So 3d, count 1, 2, 3, 4, 5, 6. This will be a 3d6. Okay. What I want you to do, you can try gold, go for gold, but why don't you also, for me, why don't you do, let's say, arsenic? So everybody, I want you to try arsenic, and we'll do that tomorrow as a class, and we'll talk about some of the other ways we can write our configurations. We will see you tomorrow.